Thanks, Jose. Nice to speak to everyone. I'll pick up where Rule left off. So can you see my screen here?
Crystal clear.
Yeah, very good. Thanks. So we basically take many of the devices that are coming out of the foundries Rule has just spoken about and packaging those. So also, as Rule had mentioned earlier, many of these devices are used in communications, like in data centers and telecommunication applications. But more and more, we're beginning to see these integrated photonic chips essentially being used in sensing, LiDAR for automotive, but also for medical devices. So as you can see, in packaging a device, there's quite a bit in there. There's optics, micro optics. In some situations with silicon in particular, you need to integrate a laser because it doesn't have its own integrated or intrinsic source. Photonics alone is no good. It has to have control electronics. It needs electrical interfaces to actually control it then. You need to, they can generate a lot of heat and are sensitive to heat. So that's something that needs to be considered. And then there's the actual application. This is actually used in a fiber sensing aerospace application, this particular package. And then you got the circuits themselves, the photonic circuits. So there's a lot in there, and it can be very complex and relatively expensive. The build cost for packaging can be over half, if not a lot more, from an assembly perspective. And that really goes to scales with volume, then it can drop considerably. One of the challenges with medical is that, you see variations in the requirements, and it may not be standardized, as easily standardized as in the communications world. So much like MedFab, we have a pilot line, it's called PIXAPP. So you can see here the website at the bottom, pixapp.eu. And essentially it's a packaging pilot line, and it's been running for 4 years, funded for 4 years, but it's basically the idea is it becomes sustainable after that period of time, which it will. And what we have here in Cork and Tyndall is an office, we call it the Gateway. So through the Gateway, people can contact us, customers, industry can contact us, and we can address their packaging requirements, be that in communications or medical, a whole array. And we've actually engaged with well over 100 companies over the past number of years, and that's growing. So it really helps us become sustainable. Now, in our packaging pilot line, we make, as Rule mentioned earlier, a lot of communication devices. So this is like a data communication system. You can see silicon photonics. Again, as Rule had mentioned, coming out of these very expensive clean rooms. But then we integrate a lot of optics and electronics, as I mentioned earlier on. But what's important here is you can take that skill set, or those building blocks, as we call them, and start to use those for medical applications. So they may be in a slightly different form, but the principles generally stay the same. Another very important aspect is that these can be very complex, as you've seen. So we really need rules around that and standards. And to date, especially around packaging, there's been very little standardization. So we've been working a lot to standardize that, not just at Tyndall, but across Europe, and also with institutes in the US. AIM Photonics is another very large photonics consortium. So more recently, we've been working with groups like that to kind of more move towards global standards. And that's not just for communications, but we're also looking at medical applications. So obviously some of the projects I cannot talk about because they're commercially sensitive, but we do have public funded programs and some more projects we can talk about in the public domain. Some of those are EU projects. But they kind of tend to fall in a number of categories, things like catheters, which is a very important platform. So much like a photonic package assembly for communications, we see a catheter as another platform for integrating photonics. Things like surgical guidance and imaging, and we work in projects in that space. So that could be for spectroscopic imaging on a surgical tool, for example, a surgical cutting device or a probing device, or for imaging as well. So not just spectroscopy, but also kind of micro camera integration. So micro cameras are becoming really, really compact and small, integrating proper illumination sources and so forth. We're starting to work in those areas as well. So one that we worked on a number of years ago with a large medical device company, and again, this is in the public domain, we were integrating optical sensors on guide wires. So guide wire, most of you are probably familiar with those, used in cardiovascular type, inserting things like stents and so forth. And in this particular project, we integrated a fiber sensor. It was actually for measuring blood flow using Doppler velocimetry. So basically feedback into an optical system, you interrogate the beam, and based on the Doppler shift from the blood cells, you can monitor the flow. So it's like a simple sensor. The important point here is, again, it's a platform. So it's integrating optical fibers onto an extremely small and flexible guide wire. So it could also be a catheter, and using that as a sensing platform. So basically what you see here is this is a guide wire. So we worked with the manufacturer of guide wires where they were able to machine out a very small little groove along the actual guide wire. So it had to maintain its kind of flexibility, or its, the torsion, so the surgeon can actually still manipulate the guide wire as they insert that up along the kind of artery or the vascular system. And what we have here is we've got these very narrow core fibers. So these are bend insensitive fibers, are pretty much bend insensitive. And because of, as you're bending these through the kind of vascular system, you don't want light to leak out across a bend. So these would be about 50 micron diameter. So again, this region here is about, say, 300, 340 micron diameter guide wire. And the core where the light is guided is about 3 microns. So these are high numerical aperture fibers. And we integrated that onto a guide wire, and then we use micro-optics again to what we call side fire. So this basically interrogates the blood as it passes through or over this region. And we were able to test that in laboratory in a microfluidic or fluidic system using real blood samples, and characterize the blood flow. Worked quite well. What's important in this particular application, we were able to develop a very nice micro-optical connector. So we use micro-optics for data center applications, but this was actually one of our first ventures into using micro lenses on a very small high NA fiber. As I mentioned, the core is around 3 microns. So it enables the surgeon to disconnect the actual the guide wire, and put a stent, for example, over that and push it through, and then reconnect it to the analyzer, if you will. So this is a very low loss and pluggable single mode connector. So again, it's using our skills in packaging and micro-optics packaging that normally come out of telecommunications, and utilizing that for medical applications. Another example here is an interrogator, where we have a similar high NA fiber, and using silicon micro lenses, which are often used in, as I say, in data communication systems. But the silicon is nice because as it's inserted into a kind of a fluidic environment, the refractive index, you maintain a certain focusing power, and you can use that for different types of sensing applications. Now, granted, silicon only is transparent above a certain wavelength, but for many applications, you can use standardized wavelengths around, say, the 1550 or 1300 nanometer, where a lot of optical sources are available. So these types of technologies we've developed and used them in catheter type applications. Just other areas where packaging, quite sophisticated packaging, comes in. This is a European project with Carl Zeiss as one of the partners, where we're integrating these silicon nitride chips with micro-optics, you can see here, bringing in a laser source. And this is used in OCT imaging, optical coherence tomography, and again, developing these very compact rather than these large-scale systems. And this is used in analysis of the eye. So looking at things like thickening of the blood vessels can be a marker for different types of diseases. Finally, as Roel mentioned, we're working with Roel previously in a project called CARDIS, and a new project called InSight, where we're integrating lasers. And the new project is looking at better ways to do that, but it enables us to use the silicon chips made with Roel's team to integrate lasers. So as I said earlier, silicon doesn't have an intrinsic light source. So this is one way of doing it. And then to produce these prototypes for this type of stenosis, kind of monitoring of the artery kind of hardness. So this is an infrared sensor. And again, it's something we can do. We can build these prototypes, and through our pilot line, we can bring them to larger scale production. So I'll leave it at that and open it for questions. Thanks.